Welcome back. In this video, we are going to solve exercises 4 to 8 of chapter 1, and they constitute a review of the topology of the real line, and we encountered some of them last semester. So it's always good to refresh, maybe because now you can revisit them in a new light. So first exercise, you have to show that the set of integers is closed in the real line. So when I say nothing, once again, it means that we equip R with the usual distance. Okay, so how to prove that a set is closed? We have at least two methodologies. The first one is to go back to the definition and prove that the complement is closed. How do I prove that? Here we have several options. Either we prove that it's a union of open sets, or we prove that it is a neighborhood of all its points. Same idea, actually. And the other methodology is to prove that it is equal to its closure. So we take a point in the closure and prove that it's in the set. Okay, so we'll explore all these possibilities, and you choose the one you like. Okay, so first way. How do we prove that the complement is open? We take an arbitrary point and in the complement, so a point which is not an integer, and we prove that it is contained in some open set contained in the complement. Okay, so take a non-integer real number and take, for example, m to be the floor function of x. So this is the biggest integer which is less or equal than x. So x will always be between m and m plus 1. But since it's not an integer, then it is strictly between m and m plus 1 because it's not an integer. Okay, and therefore, now the interval m plus 1 contains no integer, right? Because it's open. So it's totally contained in the complement of z. So this is now a neighborhood of x, or an open set containing x contained in R without z. So this precisely means that R of z is a neighborhood of x, because it contains an open set containing x. Okay, second way, same idea, but written in a slightly different way. Okay, the reasoning that we did here permits us to prove that the complement of z can be written as a union, as the union of all intervals of the form n plus 1. Okay, so note that if we close these bounds, we get R. But when we open them, we remove all the integers. Okay, how do we prove that? Double inclusion. It's very easy. So the same idea used here proves this identity. And therefore, R without Z is a union of open intervals, and therefore it's open, and therefore Z is closed. Okay, so easy enough. Now, the third way is to prove that it's the closure of Z is contained in Z. Okay. Now, this is interesting because it reveals a very important property of the integers. A convergent sequence of integers is eventually constant. What do I mean by that? It means that starting from a certain rank, the sequence stops. Okay, it becomes equal to its limit. This is a very particular kind of convergence. Okay, why do we have that? So we prove this lemma, if you like. So maybe you probably encountered this before, and it's intuitively clear. Okay, so consider a sequence xn of integers that converges. Okay, then in particular, it's a Cauchy sequence. Okay. And what does it mean that it's a Cauchy sequence? It means this is the condition here. So it means that the distance between any two terms can be made less than any positive number I like, starting from a certain rank. And this is just a consequence of the convergence. Okay? Because if you go back to the definition of convergence, if x is the limit, then xn minus x will be less than, for example, epsilon over 2. And then if you apply the triangle inequality, you get this condition. So every convergent sequence is Cauchy. Okay? And now the converse is, if the converse is true, then you say that the space is complete, and we shall devote a whole chapter on completeness. Okay, but we know that R is complete. But you don't need that. You just need a direct consequence of the fact of convergence. Okay, and this is also should be intuitively clear. If Xn is convergent, then all the elements of the sequence should accumulate around some point. So the distance between them can be made arbitrarily small. Okay. Now, in particular, if you take epsilon equal 1/2, okay, in this condition, and take m to be n0, then the distance between xn and xn0 will be less than 1/2. Okay, so this, what does it mean that, and these two are integers, okay? Now, if two integers are different, then their difference is at least 1, because between let us say k and k plus 1 or k and k minus 1, there's no integer. So if the distance between two integers is less than 1/2, then necessarily the two integers coincide. Okay? And that's it. This proves the lemma. So starting from n0, xn is equal to xn0. Okay? And since xn is convergent, then the limit must be xn0. Okay? So it stabilizes at xn0. So easy enough. Okay, and this is what I mean by eventually constant. Okay. Now we go to the proof that Z is closed by proving that it's equal to its closure. Okay. How do I prove that? Now, of course, Z is contained in its closure, so we just have to prove the reverse inclusion. So we have to prove that Z bar is contained in Z. How to prove that? We take an arbitrary element in Z bar. Now, by proposition 1.8, there is a sequence xn of Z converging to X. Okay. And by the lemma, then xn is equal to the limit that achieves the limit for n large enough. Okay. And now, since xn is an integer, then x is an integer. So we took an arbitrary element in Z bar, and we proved that it must be in Z, and therefore we have Z bar contained in Z, and so we have equality, and therefore Z is closed. Okay. So maybe you find this a little bit lengthier than the first and second way, but there's an important idea which is useful. It shows us that the convergent sequence of integers is very special. Okay. Fifth exercise, second exercise, we consider the set of inverses of the positive integers. So the set, it's the countable set consisting of 1, 1/2, 1/3, 1/4, and so on. So it's an infinite countable set. We have to show that this set is not closed, but if we add the singleton 0, it becomes closed. And third question, we have to find what is a bar. Okay. Now, why it's not closed? This is very easy, because if you consider the sequence defined by 1/n, then this sequence converges to 0. But 0 is an A bar, but not an A. So A is not closed. Okay? Because we said that if a set is closed, then and we have a sequence in A, then the limit must be in A. But here the limit is not in A. Okay, so A is not closed. Now, the second point. Okay, so you can write this idea in several ways. So 0 is an A bar, but it's not in A, so A is different from A bar, and so A is not closed. Okay. Second point, a little bit more difficult. We have to prove that A union the singleton 0 is closed. Okay. Now, the easiest thing to do here is to prove that the complement of the set is open. Okay. So call the set B. So we have to prove that the complement of B, that we can denote it by R without B or B to this BC. So we have several notations for complements. Okay. How do we prove that? We prove that BC is a neighborhood of all its points. So we take an arbitrary element not in B. If it's not in B, then it's not in A and not in 0. So it's different from all inverses of the integer because it's not in A, and it's different from 0. Okay, and here we distinguish between three cases. If x is different from 0, then either x is negative or, so we distinguish between three cases. If x is negative, then x belongs to the interval, the open interval minus infinity 0 open. And minus infinity 0 open is contained in the complement of B, because any element here, any negative number, is not in A, because A consists of positive numbers. So, and it's not 0, because I excluded 0. So this whole interval is contained in the complement. Okay, so if x is negative, then BC contains an open set containing x, and therefore BC is a neighborhood of x. Okay, this is the first case. Okay. Now, if x is bigger than 1, so any number strictly bigger than 1 cannot be in A. Okay, because all the elements in A are less than 1. Therefore, this whole this interval 1 infinity is contained in the complement, and of course cannot be 0. So any element in 1 infinity is contained in BC, okay? Because cannot be in A, cannot be in 0. And this interval contains x, so once again you have that BC is a neighborhood of x. Now, what if x is strictly between 0 and 1? Of course, I have to remove 0 and 1 because okay, x is different from 0 and it cannot be equal to 1, because if I take n equal 1, okay, x is different from 1. So it's strictly in between. Because 0 and 1 belong to B. Okay, it cannot be in BC. Okay, what happens here? If we take m to be the floor function of 1 over x, then 1 over x is between m and m plus 1. So x is between, I reversed the order here, pay attention. So x is between 1 over m plus 1 and 1 over m, and strictly. Why strictly? Because x is not is different from all the integers, 1 over it's different from all the numbers of the form 1 over n. So it cannot be equal to this one, for example. So, and now this interval 1 over m plus 1, 1 over m does not meet A, okay? Because if you draw a picture, the elements of A are 1, 1/2, 1/3, etc. So they can be listed in a sequence, in a decreasing sequence converging to 0. So between two elements, okay, so here if you like, 1 over m is strictly less than 1 over m minus 1 and so on, and 1 over m plus 1 is bigger than 1 over m plus 2 and so on, okay? So all the elements of A are outside this interval, okay? And therefore this interval is contained in the complement, and of course cannot 0, so it's contained in the complement of B. Okay, and so we have now, so once again, BC is a neighborhood of x because BC contains this interval which contains x, and that. So in all cases, we can find an open set, or in this case, an open interval containing x and contained in the complement of B. Okay, so BC is open, and therefore B is closed. And now, the ideas that we used in this proof show that BC can be written as the union of all these intervals. Okay, how do I prove that? Double inclusion. Okay, so BC, if an element x is in BC, it's either here or in one of these intervals. Okay, and conversely, of course, all these intervals are contained in BC, so we have equality. And so this is another way of saying that BC is open. Why it's open? Because it's clear now that it's a union of open sets, of open intervals. So BC is open, and therefore B is closed. Okay. Now, the other methodology of proving that B is closed by proving that it's equal to its closure is a little bit cumbersome to write. So I didn't use it. Okay. So this is easier actually. And last point, okay, so here, since A union 0 is closed, we conjecture that it's equal actually to the closure of A. Okay, so how do you prove that? Double inclusion. A union 0 contains A, but A bar is the smallest closed set containing A, and therefore A union 0 contains A bar. Okay, So what do we have? Yeah, this is actually, there's an error here. This should be, I meant to say here, A is contained in A union 0, and A union 0 yeah, there was an error in the writing. So we said that A union 0 is closed, and of course it contains A, therefore it contains the closure of A. So we can write A bar is contained in A union 0 because this is the smallest closed set containing A. Now, for the reverse, we would like to prove the reverse inclusion, but this is now easy because we know that 0 is an A bar because 0 is a limit of the sequence in A. And of course, A is contained in A bar, so the union is an A bar. So union of A and 0 is an A bar, so we have double inclusion and therefore equality. Okay, easy enough. Exercise 6. If A is bounded, if A is a subset of R, we know that, and which is bounded from above, we know that it has a supremum. We have to show that the supremum, and you know that the supremum need not be a maximum. So the supremum need not be in A, but at least it's in A bar. So it's not very far from A. And similarly for the infimum. Okay. This is very easy actually, because this follows from the characterization of the closure of a set, which is proposition 1.8. So if we want to show that sup A is in A bar, then we have to show that any interval of center sup A meets capital A. Okay, so for every epsilon positive, this is the ball of center sup A and radius epsilon. So why is there a number in A and in this interval? Okay, this is very easy. This is a consequence of the definition of the supremum. Okay, so the supremum is the smallest upper bound. So anything smaller is not an upper bound. So if you take epsilon positive, we know that there exists an element x in A which is bigger than sup A minus epsilon. Okay, so this translates the fact that sup A minus epsilon is not an upper bound. Okay, and therefore this x, and of course x is less than the supremum because the supremum is an upper bound. Okay, so actually this element x is in the interval sup A minus epsilon sup A. Okay, and of course this interval is contained in the bigger interval sup A minus epsilon sup A plus epsilon. So the intersection is not empty. And that's it. And by proposition 1.8, it follows that there is a sequence, since sup A is an A bar, there is always a sequence xn in A that converges to the supremum. And this is a very important fact in analysis. Okay. And for the infimum, it's the same thing actually, just mirror image of this. So the inf is the biggest lower bound, so anything bigger is not a lower bound. So if epsilon is given, inf A plus epsilon is not a lower bound, so I can find an element in A which is less than inf A plus epsilon. Okay, and therefore x is in the and of course x is bigger than the infimum or equal, and therefore x is in this interval, semi-open interval, which is contained in the bigger interval inf A minus epsilon, inf A plus epsilon. So the intersection is not empty, no matter how epsilon is small. And once again, it follows that there is a sequence xn of A converging to the infimum. A very important fundamental fact in analysis. Exercise 7. We are given two sets of the real line. The first set A is the set of all the rational numbers between radical 2 and radical 3. Of course, I can open radical 3 here because radical 3 is not in Q. So, and the second thing is, the second set is the set of irrational numbers between 0 and 1. So once again, I can open this here. It doesn't change anything. We have to find the interior, the closure, and the closures of these sets. Okay. Now, the interior of A is very easy to find because A is a subset of the rational numbers. So the interior of A, let me say something because I need it in the proof, okay, later. It's a consequence of proposition 1.8 that I didn't do in the lectures. So if A is a subset of a metric space, we know proposition 1.8 tells us that there's equivalence between X belongs to A bar, every neighborhood of X meets A, and there is a sequence in A converging to X. Now, this is also equivalent to another condition, slightly different than condition 2 in the proposition. So instead of every neighborhood of X, I can take any sufficiently small neighborhood of X. So this condition, every neighborhood of X meets A, is equivalent to saying that any ball of center X meets A. So for every epsilon positive, the ball of center X and radius epsilon intersects A. But I can replace this by another condition which states that there exists epsilon 0 positive such that every ball of center epsilon less or equal than epsilon 0 meets A. So you see that they are related. Here there's no restriction on epsilon. Here there is a restriction on epsilon. Okay? So, and otherwise stated in words, if you like, every small enough neighborhood of X meets A, or every small enough ball of center X meets A. Okay, now of course, 1 implies 2, because here there's no restriction on the ball. But 2 implies 1, actually. So, and this is very useful in practice, because sometimes you need to take small balls, okay, smaller than, with radius small enough. You'll see why we need that, and this is very general. Okay, so why 2 implies 1? Okay, let epsilon 0 be as in condition 2. Okay, it's given by the condition. Now we'll give an example. And now let epsilon be an arbitrary positive number. Okay, so it could be smaller than epsilon 0 or bigger. Okay, so we distinguish between two cases. If epsilon 0 is less or equal than, if epsilon is less or equal than this bound epsilon 0, then by assumption 2, the ball of center X and radius epsilon meets A. So there's nothing to prove. And if epsilon is bigger than epsilon 0, then the ball of center X and radius epsilon 0 is contained in the ball of center X and radius epsilon because it has a bigger radius, same center. So the intersection with A is contained in the intersection of A. But by assumption, the smaller ball meets A. So this is not empty, and therefore the bigger set is not empty. Pretty straightforward. Okay. And we have a similar situation when you want to prove the continuity of a function. You know the definition was epsilon and delta. So a function is continuous at the point X if whenever y is close enough to X, f of y minus f of X is less than epsilon. And here once again, it's enough to prove that for epsilon smaller than a given bound epsilon 0. Same principle. Okay, so it looks different, but it's actually the same thing. And now you would see why I formulated this useful result. Okay. Okay, so now we go back to the exercise. The interior of A is easy to find because the interior of A is contained in Q. So the interior of A is contained in the interior of Q by the previous video, and therefore the interior of A is empty. So straightforward. Now, the closure, little bit more complicated to prove. So first of all, A is contained in the closed interval radical 2, radical 3, and therefore A bar is contained in that same interval. Okay. And now, since Q is dense, you'd like to prove that you have equality here. Okay, so this is the idea. But how to prove that? We take an element here and we prove that it's an A bar. So every neighborhood of that, so use once again proposition 1.8. So we take an element in radical 2, radical 3, closed, and we want to prove that every neighborhood of X meets A. So we distinguish between, and by the remark that I said, it's enough to prove that every small enough neighborhood of X meets A. You will see why I need this restriction on the small neighborhood. So distinguish between three cases. First case, X is strictly between radical 2 and radical 3. Since radical 2, radical 3 is an open interval, it's an open set. So we know that there exists epsilon 0 such that the interval of center X and radius epsilon 0 is contained in radical 2, radical 3. We did that in details last semester, and we reprove it this year. if you like, epsilon 0 is the distance between x and the endpoints. Okay. So there's a formula for epsilon 0. We can take epsilon 0 as big as possible, actually. Okay, so therefore, now we take epsilon, a positive number epsilon less or equal than epsilon 0. So what do we have? Therefore, x minus epsilon, x plus epsilon is contained in this interval, x minus epsilon 0, x plus epsilon 0. And therefore, it's contained in radical 2, radical 3. And now, this is an open interval, which is not empty. So it contains a rational number. Okay, so pick a rational number in this interval. What happens now? Then this rational number is of course in Q, and it's in radical 2, radical 3. And therefore, it's in A, and by our choice, it's in the interval x minus epsilon, x plus epsilon. So we found an element in x minus epsilon, x plus epsilon, and in A. So the intersection is not empty. And by proposition 1.8, x belongs to A bar. Okay. Second case, x is one of the endpoints. For example, suppose it's radical 2. Okay. We take a positive number, epsilon 0, which is less, or could be taken to be equal, actually, it doesn't matter. So epsilon 0 is small enough, so less than the length of the interval, radical 2, radical 3. Okay, then the open interval of endpoints x and x plus epsilon 0 is by construction contained in radical 2, radical 3 open, okay, because x is radical 2 here. Okay, so radical 2 plus epsilon 0 is contained in radical 2, radical 3 because epsilon 0 is less than radical 3 minus radical 2. So radical 2 plus epsilon 0 is less than radical 3. So by construction, this is actually, you can draw a picture here. Okay, so this interval x plus epsilon 0 is contained in the open interval radical 2, radical 3, and therefore, if we take epsilon to be a positive number less than epsilon 0, this still smaller interval x plus epsilon is contained in x plus epsilon 0, and so it's contained in radical 2, radical 3. And now you guess what I want to do. I just choose a rational number y in this small interval x plus epsilon. Therefore, this y is in particular in x minus epsilon, x plus epsilon, and it's in A because it's rational and in the interval radical 2, radical 3. And therefore, the intersection is not empty. Okay, and the last case is totally symmetric. If you take x to be radical 3, just repeat the same thing, but take, so once again, we take epsilon 0 equal radical 3 minus radical 2, and there we should change a little bit. Instead of x plus epsilon, we need to take x minus epsilon 0 x, because it's symmetric, it's the complete. So it may be very helpful to draw figures, actually, just on straight line and see what happens, what we are. Okay, so a little bit cumbersome to write, but it's not so difficult. So okay, and therefore we proved that the reverse. So any point here is in A bar, so A bar is radical 2, radical 3 closed. Okay, and now for B, it's completely similar. So once again, B circle, the interior of B is empty because the interior of the irrational numbers is empty, and B bar is 0, 1 closed. So just the same idea, but instead of choosing a rational number here in this reasoning, choose an irrational number, because we know that every non-empty open interval contains rational numbers as well as irrational numbers. So just train yourself to write this, just copy paste. Okay, so this concludes exercise 7. And now the last exercise about density. We are given 3 sets: Q, the rational numbers union radical 2, which is not in Q, Q without 1, and Q without the integers. Okay, which one is dense? Actually, all of them is dense. The first one is easy because this set contains Q, and Q is dense, therefore this set is dense. So here we have a general principle. Any set containing a dense set is dense itself. Why? Because if Q is contained in this, then Q bar is contained in the closure of this. But Q bar is R, so R is contained in the closure of this. So we have double inclusion, and therefore we have equality. Okay, so if the smaller set is dense, the biggest set is dense. Okay, this is straightforward. Now, Q without 1 is less trivial. Okay, because here Q without 1 is contained in Q, so it's a smaller subset. And same thing for Q without Z. Okay, so here we use once again proposition 1.8, the characterization of the closure. So how do you prove that, or the corollary of it? How do you prove that a set is dense? You have to prove that every non-empty open set meets Q without 1. So take an open non-empty, can take it to be an interval, actually, doesn't matter, or just an open set, it doesn't matter, because any non-empty open set contains an interval. So saying that any non-empty interval meets Q without 1 is the same thing as saying every non-empty open set meets Q without 1. So same thing. Okay, so we distinguish here between two cases. If 1 is not in that open interval, then the intersection of I and Q without 1 is the same as the intersection of I and Q. Because why? Because you can write this as I intersected with Q intersected with the complement of 1. But since 1 is not in I, then I is contained in the complement of 1. So I intersected with the complement of 1 is I. So, and okay, there are several ways to see this. This is a set theoretic identity. So this is very general. Okay. And there's another way to prove that. So you take an element, of course, this is contained in that, and conversely, if you take an element here, X, then X is in I, but if it's in I, it cannot be equal to 1, because 1 is not in I. So the element X is in Q without 1. So same thing. So very easy. So if 1 is not in I, then this interval meets Q without 1, and therefore, so this is the first case. Now, what if 1 is an I? It's not a big deal, because if 1 is an I and I is open, we can find an open interval of center 1 contained in I. And now it's very easy. Now, this open interval contains a rational number different from 1. Okay, because actually the 1 is not the unique. 1 is rational, but in this interval there are infinitely many rational numbers. So just take 1 different from 1. Okay, or just, if you'd like, take a rational number strictly between 1 and 1 plus epsilon, doesn't matter. And that's it. So this element, this rational number that called y actually, is an I, because it's in the interval, and it's different from 1, so it's Q different from 1. So the intersection is not empty. So in all cases, this open interval meets Q without 1. So by a corollary of proposition 1.8, Q without 1 is dense. And for the first set, the idea is similar. Okay, so we take a non-empty open interval and distinguish between two cases. If this open interval doesn't contain integers, so the intersection of the integers is empty, then as you may check, the intersection with I and Q without Z is the same as I without Q, intersected with Q, double inclusion, because this is contained in this. And now, if we take an element X here, then X is in I and Q, so it's here. But if X is in Q is in I, it's not an integer, because the intersection is empty. So an element X here is not an integer, and therefore it's irrational but not an integer. So it's here. So double inclusion, and therefore, and this is not empty because Q is dense. Okay, same thing here. Now, if not, take an integer in the intersection, call it M, and since I is open, there is a number epsilon positive. We can take as small as we wish, actually. Just take it smaller than 1, such that the interval M minus epsilon M plus epsilon is contained in the open interval I. And now, since what are the integers actually in this? What are the integers in this interval? Okay, so epsilon is less than 1. So the only integer in this interval is just M. Okay, and since there are infinitely many rational numbers in this interval, choose one which is different from M. Okay, even if we have 2, actually, because we have infinitely many. So choose a rational number in this interval, but different from m. Okay? You can take it strictly between m and m plus epsilon, doesn't matter. And now this element is a rational number, not in Z, it's in I, so it belongs to the intersection, and therefore the intersection is not empty. Okay? So any non-empty open interval meets Q without Z, and therefore Q without Z is dense in R. Okay, so this concludes exercise 8 and the video. Thank you for your attention, and see you in the next video.